Hello, everybody, and welcome to today's live stream. I'm the Shy Hat, and we're going to be doing day 6 of TryHackMe's Advent of Cyber challenges. All right, so for everybody who's just tuning in and wants to join in, I have a link that you can follow. If you follow this link, you will be able to see the challenges, the room that we are working inside of, and hopefully participate in the challenge yourself. All right. So without further ado, let's get started. All right. So we're talking about memory corruption today. What are our learning objectives? Today we're going to understand how specific languages may not handle memory safely. We're going to understand how variables might overflow into adjacent memory and corrupt it. We're going to exploit a simple buffer overflow to directly change memory you're not supposed to access, and that's what we're going to do. So before we move forward, we're going to see what we need to do to complete today's task. Do we need to start the attack box today? No. Do we need to start a VM today? Yes. Is there a split screen available? No. Is there a direct link available? Yes. Are we given credentials to connect directly to a VM via RDP, VNC, or SSH? No. Okay, so what we need to do is we need to go up to the green Start Machine button over here under Task 12, Day 6, and click on that. And then our virtual machine for today's challenge is going to initialize. So we see here that it's going to initialize in roughly a minute. So we're going to wait on that. But while we're waiting for that, we're going to take a look at what's going to go on with what we're going to deal with today. All right. So what we're dealing with is a game. So we're going to do some game hacking today. In this game, we're going to play as cat or mouse. Okay, your objective is to save Christmas by buying the star for the Christmas tree from Van Frosty. Okay, in addition to the star, you can buy as many ornaments as you can carry to decorate your tree to gain money to buy things. You can use the computer to do online freelance programming jobs. All right. You can also spend to speak to Van Holly to change your name for a fee of 1 coin per character. He says that this is totally not a scam. He will actually start calling you by your new name. He is, after all, into identity management. All right, so is this a bug? Before the training even starts, Van Jolly approaches McHoneybell and says that they've been observing some weird behaviors while playing the game. They think the ghost of Christmas past is haunting it. Okay, McHoneybell asks them to reproduce what they saw. Van Jolly boots up the game and does the following, which you're free to replicate too. Use the computer until you get 13 coins. Ask Van Holly to change your name to Scroogedrocks! And suddenly you have 33 coins out of nowhere. So let's go up to here where we can see that there's a link. So this link is not going to be the same for everybody, but you can use your link and copy this with the Control-C button. And then we're going to go to a new tab. We're going to go to a new tab and we're going to paste the link in. Okay, so we see that this is a web application. We can press space to continue. And we get the game controls over here. So we can use the arrow buttons to move. We can use the space bar to interact and speak. We can press tab to get the debug panel. And we can press backspace to reset the inventory. And we can press space to continue. Okay, to finish the game, all you need to do is get a star to put on your Christmas tree. After you get the star, just interact with the Christmas tree, and that's it. You are free to buy as many additional ornaments as you can carry to customize your tree. Okay, so let's see if we can enlarge the game somehow. Maybe we can, maybe we can't. Okay, maybe we just can't. Okay, so I hope you can bear with me as we look at this slightly smaller display than we prefer. Okay, so what do we do to recreate that bug? Okay, we have to use the computer until you get 13 coins. You have to ask Van Holly to change your name to Scroodrox, exclamation point, and then you have 33 coins. So, in the game, we can go here and we can press the computer 13 times until we have 13 coins. Oh, we can just hold down the space bar. Okay, so once we have 13 coins, we can go up to this character right here, and we can change our name for 1 coin per character. And then we're going to change our name to Scroodrox, exclamation point, and return. And then suddenly we have 33 coins over here. All right, so what happened? Let's take a look at the explanation here. Vangelis explains that when you change your name to anything large enough, the game goes nuts. Sometimes you'll get random items in your inventory or your coins just disappear. Even the dialogue can stop working and show random gibberish. This must surely be a work of magic. McHoneybell doesn't look convinced. After some thinking, she seems to know what this is all about. Okay, so we're talking about memory corruption in today's task. Remember that when we execute a program, this game included, all data will be processed somewhere through the computer's RAM, random access memory. In this video game, your coin count, inventory, position, movement speed, and direction are all stored somewhere in the memory and are updated as needed as the game goes on. So we can see here a visualization of the game's memory and where various game statistics are stored inside of the game's memory in blocks. So for example, your character's position, y coordinates, x coordinates are mapped over here. The number of coins that you have is mapped over here, and some other stuff is mapped all over the memory space. Usually each variable stored in memory can only be manipulated in specific ways as the developers intended. For example, you should only be able to modify your coins by working on the PC or spending money either at the store or by changing your name. In a well-programmed game, you shouldn't be able to influence your coins in any other way. But what happens if we can indirectly change the contents of the memory space that holds the coin count? What if the game had a flaw that allows you to overwrite pieces of memory that you're not supposed to? Memory corruption vulnerabilities will allow you to do that and much more. Honeybell says a debugger will be needed to check the memory contents while the game runs. On hearing that, Van Sprinkle say that they've programmed a debug panel into the game that does exactly that. That'll make it easier for us. All right, so accessing the debug panel. While they were developing the game, the Frostlings added debugging functionality to watch the memory layout of some of the game's variables. They did this because they couldn't understand why the game was suddenly crashing or behaving strangely. To access this hidden memory monitor, just press Tab in the game. You can press Tab repeatedly to cycle through 2 different views of the debugging interface. The ASCII view, the memory contents will be shown in ASCII encoding. It is useful when trying to read data stored as strings. Or in hex view. The memory contents will be shown in hex, as in hexadecimal 16-character counting system. This is useful for cases where the data you are trying to monitor is a raw number or other data that can't be represented as ASCII strings. Okay, so we can see that this is an example of the debug screen. Okay, we have one in ASCII and another one in hex. So we can see that there are a bunch of different variables that we're working with. There's the player name, coins, the shopkeeper name, the name changer person name, our inventory items, and the inventory is rare, the variables. All right, so we can see that by default, okay, we are cat or mouse as the player name. The coins are set as 0. The shopkeeper name is Van Frosty. The name changer name is Van Holly. The inventory items here, this is one, which is some item. I'm not sure exactly what. And we can see here that the same values are represented here, but in hexadecimal form. Viewing the contents in RAM will prove useful for understanding how memory corruption occurs, so be sure to check the debug panel for each action you make in the game. Remember, you can always hide the debug panel by pressing Tab until it closes. Okay, so we're going to investigate this Scroogedrox case. Armed with the debugging panel, McKenniebell starts a lesson. As the first step, she asks you to restart your game. Refreshing the web page should work, and open the debug interface in hex mode. Alright, so we go to the game, and we're going to reload the page. And we're going to start it again. And if we press the Tab key, we can see the debug screen right over here. Okay, in hex mode, so the first tab is going to open it in ASCII mode, and the next one is going to open up in text mode. So we press Tab again, and we see the values in hex mode over here. McKenniebell wants you to focus attention to the coins variable. Go to the computer and generate a coin. As expected, you should see this coin count increase in the user interface and the debug panel simultaneously. Okay, so if we see here, and we walk up to the computer, coins is at 1 right now, and coins is 1 on the hex counter here. If we press if we press space once in front of the computer, we see that the number of coins over here and over here have both increased to 2. All right, so that works. Okay, as expected, you should see the coin count increase in the user face and the debug panel simultaneously. We now know where the coin count is being stored. McKenniebell then points out that right before the coins memory space, we have the player name variable. Okay, so if we look here, we see right before the coins counter, we have the player name variable up here. The player name variable up here, all right. She also notes that the player name variable only has room to accommodate 12 bytes of information. But why does this matter at all? Because if you try to change your name to Scroogedrox, you would be using 13 characters, which amounts to 13 bytes. Okay, so what would happen with the extra byte at the end? It will overflow to the first byte of the coins variable. To prove this point, McKenniebell proposes replicating the same experiment, but this time we will get 13 coins and change our names to AAAA, BBBB, CCCC, and X. Okay, so let's try this out. So first we need to get 13 coins from the computer, so we'll hold down the space button in front of the computer. And we slowly see the number of coins increasing over at the top of the screen over here. Okay, so we have 13 coins. Okay, so then we change our names to AAAA, BBBB, CCCC, X. Okay, let's do that. So we move up to this character over here, and then we press space, and we change our names. So it's going to be AAAA, BBBB, CCCC, DDD. Oh, sorry, and the last one is X. Is it a small x or a big X? It's a small x. So this actually makes a difference inside of these kind of memory issues. So small x, return, and suddenly we have 120 coins over here. Okay, all of a sudden we have 120 coins, and the memory space of coins variable now holds the value 78. Okay, so we can see here that indeed the coins value over here is at 78 in the hex view. Okay, we have to remember that in hex, 78 in hexadecimal equals 120 in regular decimal numbers. To make this even clearer, we can switch the debug pane to ASCII mode, and we can see that the player name value over here is exactly what we set it to, but since there aren't enough spaces to hold the entire name that we selected, then the extra character is going to overflow into the coins column over here. So X, which in hexadecimal value is equal to 78, which is 120, is what we get. The X at the end of the new name split over into the coins variable, and the ASCII hexadecimal for X is 78. So the coin value was changed to 78 or 120 in decimal representation. So the X equals to 78 in hex, but in decimal, that's 120. It's a bit confusing when you think about the different conversions, but eventually you'll get used to it. So as you can see, McHoneyBell's predictions were correct. The game doesn't check if the player name variable has enough space to store the new name. Instead, it keeps writing to adjacent memory, overwriting the values of other variables. This vulnerability is known as buffer overflow and can be used to corrupt memory right next to the vulnerable variable. Buffer overflows occur in some programming languages, mostly C and C++, where the variable's boundaries aren't strict. If programmers don't check the boundaries themselves, it is possible to abuse a variable to read or write memory beyond the space initially reserved for it. Our game is written in C++. Okay, so strings in more detail. By now, the Frostings have baffled it never occurred to them that they should check the size of the variable before writing to it. Van Twinkle has another question. When the game started, the main character's name was Cat or Mouse, which only used 10 characters. Okay, so in here we see that there are 10 characters, cat or mouse, and then some zeros. So how does the game know the length of the string if no boundary checks are performed on the variable? To explain this, McHoneyBell asks us to do the following. So restart the game, get at least three coins, change your name to Elf. Okay, so inside the game we can restart the game. Okay, and then we get 3 coins, 1, 2, 3, and then we change our name to Elf. Okay, so we see that our player name is changed to Elf, and then a 0, and then our MOS or mouse, our mouse over here. So why is that? Let's read on. So as a result, the memory layout should look like this. When strings are written to memory, each character is written in order, taking 1 byte each. A null character, represented in the game by a red 0, is also concatenated at the end of the string. A null character is simply a byte with the value of hexadecimal 0x00, which can be seen by changing the debug panel to hex mode. When reading a variable as a string, the game will stop at the first null character it finds. This allows characters to store smaller strings into variables with larger capacities. Any characters appearing after the null byte are ignored, even if it has a value. To better explain all of this, McHoneyBell proposes a second experiment on strings. Get 16 coins, and then rename yourself to AAAA, BBBB, CCCC, and DDDD, which is 16 characters. Okay, let's do that. So we'll get 16 coins. Okay, it takes a little bit of time. Okay. So if we go to change our name, we can change it to AAAA, BBBB, CCCC, and DDDD. And you can see that it goes off the screen over here a little bit. And then we press return. All right, so we see in the screen here that suddenly our coins were replaced with DDDD, which in hexadecimal is 44, 44, 44, but in decimal value is this number right here, which is a really big number. Okay, so now our memory layout should look like this. So it's going to be AAA, BBB, CCC, and then in coins, the value DDDD is in its place. So notice how the game adds a null character after your 16 bytes, which overwrites the shopkeeper variable. So if you talk to the shopkeeper, you should see that his name is empty. And indeed, if we move over to the shopkeeper, we can see that the name is empty because the shopkeeper name is set as 0 right here. So 0, which means that it's empty. Okay. So going back to the lesson. So this happens because the game reads from the start of the variable up until the first null byte, which appears in the first byte in an example. Therefore, this is equivalent to having an empty string. On the other hand, if you talk to Van Holly, you should see that his own name is now AAAA, BBB, CCC, DDD, okay, which is 16 characters long. All right, so if we talk to Van Holly, which is the name character, okay, so that didn't quite work. So our own name, right? So our own name is this, right? Okay, so since C++ doesn't check variable boundaries, it leads your name from the start of the player name variable to the first null byte it finds. So this is why your name is now 16 characters long, even though the player name variable should only fit 12 bytes. Part of your name now overlaps with the coins variable, so if you need to spend some money in the shop, your visible name will also change. Buy some items and see what happens. Okay, so we're going to skip that. We're going to take a look at the next part, which is integers in the coins variable. So Van Twinkle mistyped the name during the previous experiment and ended up with this name right here. AAA, BBBB, CCCC, DEFG, and then they noticed that they had this large number of coins in the upper right corner as shown in the debug panel. Okay, so this is the hexadecimal representation of these letters right here, D, E, F, G. D is 44, E is 45, F is 46, and G is 47. So out of curiosity, they used an online tool that converts hexadecimal to decimal numbers to check if the hexadecimal number from the debug panel matched the coin count. To their surprise, the numbers were different. So if we take 44, 45, 46, and 47, and we go to the hexadecimal to decimal converter, okay, so that's 44, 45, 46, 47, and we convert it to decimal. Okay, it's going to give us this value, but 11, 45, 39, something, something, is not the same as this number over here, which is 11, 95, 95, 78, and then some other numbers. So it's different. Why? So let's take a look at the explanation. McHoneybell explains that the integers in C++ are stored in a very particular way in memory. First, integers have a fixed memory space of 4 bytes, as seen in the debug panel. Secondly, an integer's bytes are stored in reverse order in most desktop machines. This is known as little endian byte order. So to use an example to understand this better, if you take the current coin count of this and convert that number into hex, you'll obtain this number right here in hex. Okay? So for example, if we copy this number and then we go to the converter and we go from decimal to hexadecimal, decimal to hexadecimal, and we insert this number and we convert it, then it's 44, 45, 46, and 47. So this is in reverse order, 44, 45, 46, 47, instead of 44, 45, 46, 47 in the other order. So corresponding to what's shown in the debug panel, but backwards, how many coins would you have if the hex value of the coins was showing as follows? Input your answers at the end of the task. Okay, so if we have this many coins right here, we're going to figure this out at the end of the task. So we'll go over that a little later. So winning the game. McHoneybell is about to wrap up the lesson and call it a day, but first he explains how an attacker could now overwrite any value to the coins variable and have enough to buy the star and finish the game. On hearing this, McGreedy starts laughing maniacally and tells McHoneybell they rigged the game so nobody could win. McHoneybell is more than welcome to purchase a star, McGreedy says. So confused, McHoneybell does some quick calculations and concludes she should be able to get enough coins. She looks at you and asks how the vulnerability can be exploited. You notice that she looks a little doubtful, but still, it's now up to you to win the game. Can you get a star in the inventory and prove McGreedy wrong? Alright, so once you get the star, interact with the Christmas tree and finish the game. Okay, so first we're going to answer this question. If the coins variable had in-memory value of the image below, how many coins would you have in the game? So if you remember from what we learned previously, okay, so this is the hex representation, right? So we wouldn't be, and in the coins variable right here, we're reading from right to left, not left to right. So the value is not 4F, 4F, 50, 53. It's 53, 50, 4F, 4F. So if we take 53, 50, 4F, 4F, and go over here, and we select from hexadecimal to decimal, and it's 53, 50, 4F, 4F, and we convert that, we get this number right here. So we can copy this, and we can supply it as the answer. Paste it in. Submit. Okay, that's correct. So what is the value of the final flag? We need to get the star in our inventory, and we need to get the star in our inventory, and then we need to interact with the tree. So what we can do is, from the very beginning, we're going to reload the game, and we're going to do it from the start. Okay, so first we're going to get 13 coins. Actually, let's get 16 coins, just so we can get a lot of money. $13, $14, $15, $16. Okay. So we go over here, and then we change our name to A, B, 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 C, 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 D, 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 D. Okay, and then we get a lot of money. Okay, so if we were to go to the vendor over here and try to buy the star with the ID of D, we would have to type D and then press enter. Okay, they say, hey, you're not supposed to have that kind of money. The game is supposed to be invulnerable, you know? I'll cut you a deal, I'll give you a much cooler item for the same price. Okay, so we see that instead of the star that we're supposed to get, we get this nutcracker item right here, which of course we can't use to win the game. Okay, so what we're going to do is we're going to try to overflow everything in here in this memory space until we get to the inventory items. So the inventory items, and we're going to overwrite the first slot of the inventory items with a D, with the small d, which is the code for the star. Okay, so you see here that we're going to need to overflow a lot. Okay, so it's going to be A, B, C, D, E, F, G, H, I, J, K, and then the first, and then D. So it's because we need to overflow so much, it's going to be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Okay, so 11 times 4, so it's going to be 45. We're going to put in 45 characters to overflow everything in here until we get to here, and then we put the code for the star item. So we can do that right now. We go over here, we rename ourselves. So it's A, B, 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 C, 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 D, 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 E, 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 F, 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 G, 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 H, 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 I, J, 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 K, 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 and then the final character is going to be a small d. And then press enter. And then we see that in the inventory items, there is a small d, which corresponds to the star over here, which means we can now finish the game. So we go up to the tree, and then we press space, and then we see that we see the postcard here, and it says, you got the star, thanks for getting me ready for Christmas, here's your flag. Okay, so it says here, THM, McHoneybell is the real star with underscores over here, and we can use this as the flag to complete the room. So THM, curly brackets, McHoneybell is the real star, and then we separate this with their underscores. Okay, and then we press submit, and we got the answer right, and we're just about to finish this room. So it says we have only explored the service of buffer overflows in this task. Buffer overflows are the basis of many public exploits and can even be used to gain complete control of the machine. If you want to explore the subject more in depth, feel free to check out the buffer overflows room. So if you want, you can go to this room, and you can, I'm pretty sure this is a free room. You can learn more about buffer overflows over here, and we don't need to answer anything here. Just click on completed. And it says, Van Jolly still thinks the ghost of Christmas past is in the game. She says that she's seen it with her very own eyes. She thinks the ghost is guiding in a glitch, whatever that means. What could she have seen? So we're not going to be covering this in this live stream, but I think that we should be able to get access to the side quest content of this day in the event if we overflow the program until it crashes. So I'm not sure exactly how much you'd have to overflow in order to crash the program, but my guess is probably going to be somewhere in the hundreds of characters range. But if you're interested in a more advanced challenge, certainly pursue that. But we're going to complete this. Thank you very much for watching us complete day 6 of the TryHackMe Advent of Cyber Challenge. We're going to be back tomorrow, as usual, covering day 7, and we're going to be learning more beginner's cybersecurity more beginner cybersecurity skills then. But until then, everybody, have a great day, and we'll see you next time.